Class 11 Chemistry, Classification of Elements and Periodicity and Properties.
Hello, scientists, and welcome! Today, our story begins with a big question. How do we make sense of all the elements in the universe? I'm your guide on this adventure, so grab your goggles and let's dive into the classification of elements and periodicity in properties. Our story starts with a problem. There are 118 different elements, way too many to memorize one by one. So chemists wondered, what if we group elements with similar properties together? And here's the secret. An element's properties depend on its electronic configuration. For example, lithium, sodium, and potassium each have just one electron in their outer shell. That's why they're all soft, shiny metals that react fast. The first heroes of our story came in the early 1800s. Dobereiner noticed triads, groups of 3 elements where the middle one had a mass halfway between the others, like lithium, sodium, and potassium. Later, Newlands gave us the law of octaves. Every 8th element seemed similar, just like notes in a musical scale. Then came the true giant of our story, Mendeleev, in 1869. He arranged the elements by increasing atomic mass, and he did something brilliant. He left gaps in his table for elements that hadn't been discovered yet. He even predicted their properties. When gallium was found later, it matched his prediction perfectly. What a triumph! But our story wasn't finished. Moseley, in 1913, revealed the real secret. The properties of elements depend on the atomic number, not the atomic mass. This corrected the table and gave us the modern periodic law. The properties of elements are a periodic function of their atomic number. Now our story brings us to the beautiful table we use today. It has 18 groups and 7 periods. Every element finds its place by its electronic configuration in one of 4 blocks: the S block, the P block, the D block, and the F block. It's like a giant map with a home for every element. Now, let's explore the trends, the secret patterns. First, size. The atomic radius is the distance from the nucleus to the outermost shell. Across a period, the radius gets smaller because the nucleus pulls the electrons in tighter. Down a group, it gets bigger because a new shell is added. And for ions, a cation, a positive ion, is smaller than its atom, while an anion, a negative ion, is bigger. What about the noble gases, the shy loners of the table? They form no bonds, so we measure them with the van der Waals radius, which is always larger than the covalent radius. For example, neon has a covalent radius of about 38 picometers, but a van der Waals radius of about 160 picometers. Next, ionization enthalpy, the energy we need to pull away the outermost electron from a gaseous atom. Across a period, it increases. Down a group, it decreases. But watch out for surprises. Beryllium beats boron, and nitrogen beats oxygen, because half-filled and fully filled shells are extra stable. Now, electron gain enthalpy, the energy released when an atom gains an electron. Across a period, it becomes more negative, and down a group, it becomes less negative. And here's a famous twist. Chlorine actually beats fluorine because chlorine's extra electron has more room to settle in comfortably. Electronegativity is an atom's power to attract the shared pair of electrons in a bond. It increases across a period and decreases down a group. And the crown goes to fluorine, the most electronegative element of all, with a value of 4.0. Then there's valency, the combining capacity of an element, how many bonds it can make. It equals the number of valence electrons, or 8 minus that number. Across a period, valency climbs from 1 to 4, then falls back down. Down a group, it stays steady. Every halogen has a valency of 1. Finally, our story reaches the giants, elements with atomic number above 100. Since they don't have permanent names yet, IUPAC gives them temporary names. Just spell the atomic number using digit roots and add the suffix ium. For example, 104 becomes unnil quad ium, or unnil quadium, with the symbol UNQ. And that, my friends, is the story of the periodic table. Remember the trends. Across a period, size shrinks, while ionization enthalpy and electronegativity grow. Down a group, size grows, while those values shrink. Thank you for joining me on this adventure. If you enjoyed it, please like and subscribe for more chemistry stories. See you next time!
Video by Anand Mohandas.